everyone. So welcome back. We have week 10 of the coding challenge. So great to have you along with us. It's been 10 weeks already since we started. You can't imagine that, but great for all of you who have been submitting code. And tonight I have with me Ronald. Hello, Ronald.
Hello, everyone. This week we saw a lot of different approaches again, actually. Some were very simple and some were quite complex. So without further ado, let's go in and get into the nitty-gritty of them all.
Okay, sounds great. Okay, so let's walk through what the problem is for this week. So we're calling it the Nutty Squirrel. So basically, you have to find the minimum eating rate for each squirrel to maximize the squirrel's nut consumption. All right, so what does that mean? So there's various bird feeders in various homes in the neighborhood, and the squirrel needs to consume these nuts. Now, there are some constraints. The squirrel can only be at one home in each hour. So they can stay past the hour into the next hour at that home, but they can only go to a new home at the beginning of each hour. So then the eating rate, which is the number of nuts per hour, remains the same throughout the entire day. Okay, so we're supposed to find the minimum eating rate. So let's look at a quick example here. So in this example, we have 4 homes, home A, B, C, and D. Home A has 3 pounds of nuts, B has 4 pounds of nuts, and so forth. And the squirrel has 6 hours total to complete consuming all these nuts. So the answer, the minimum eating rate in this case would be, 4, right? So 4 pounds of nuts per hour. So for house A, the squirrel can finish all 3 pounds of nuts with that rate and have a little time left over before moving on to the next house. The same with house B. Now house C, because it has 5 pounds of nuts, in the first hour, the squirrel would consume 4 pounds of nuts. And then in the second hour, the squirrel would consume the remaining 1 pound of nut. And so the squirrel would be in house C for 2 hours. And then the same with house D, the squirrel would be there for 2 hours, consuming 4 pounds of nuts and 2 pounds of nuts respectively. So that uses up all 6 hours, and the minimum rate that the squirrel needs to eat is 4 pounds of nuts per hour. Okay. All right. So let's take a look at our submissions here. The first submission here is from Eric. So Ronald's going to walk us through the algorithm of Eric's code, and then we'll go back to his code.
Okay. So Eric does quite our take is that it's quite simple. So the first thing he does when he gets the inputs is that he adds up the total pounds of nuts, and then he would calculate the initial minimum eating speed by dividing the total amount that the squirrel would need to be eating by the amount of time the squirrel has. So in this example here, they have 18 pounds of nuts over 6 hours. So he gets initial minimum eating speed of 3 pounds per hour. Next, Eric does this calculation of figuring out how many hours it takes for the squirrel to eat at each house. So he calculates the 3, 4, 5, and 6 pound nut houses, and each of them are 2 hours except for the first one. And finally, he sums up the total amount of hours and compares it to see the maximum time he has. So for this, the squirrel eats it in 7 hours, but there's only 6 hours to eat it in. So that's not going to work. So what Eric does is he goes back and increases the eating speed by 1 pound an hour and does the check again. And this time the calculation equates to 6. So this is the answer that he will return.
Okay, awesome. Yeah. I thought this algorithm was kind of short and sweet, and it's pretty understandable as well.
Mhm.
Yeah. Well, do you have any critiques on the code or the algorithm itself?
No, I think I mean, I don't have too many issues with it. For the most part, like just I appreciate how it's clear and concise, really. So yeah, I really appreciate that.
Yeah. Yeah, I really like the algorithm in that it makes a lot of sense, right? You're taking a rate that you're taking an initial rate and you're dividing it into the house, each house, to see if that works, and if it doesn't, then you go to the next rate, which is one incremented one higher than the previous rate until you find the answer.
Mm-hmm.
My only little nitpick is this post increment here. Even though it works with a space, I probably wouldn't put a space in there, just because that's not normally how it's written, and it makes it very obvious when it's right beside it that which variable you're incrementing.
Mm-hmm.
That's my only nitpick, Eric. So, but other than that, great code. Just a little nitpick. Yeah, sorry. As you can tell, I'm a very picky code reviewer. Okay, so should we go on to the next one?
Yeah, let's do that.
Okay, so this next one is by William. All right, so William's works. It works really well. It gives the answer, and it's also understandable. But as you can see, it's a lot more verbose than Eric's, and it's not as understandable as Eric's, just because it has a lot more steps involved.
Mm-hmm.
Yeah. So first off, he sorts the piles here, and then there's this initial check here. This first bunch of code here to check to see if the number of piles is equal to the number of hours. If it is, then it just gets the largest number and returns that. So that's one scenario. And then there's another scenario here. And then there's a third scenario here. So the code actually has three different scenarios that it's looking at. So that's why it's not as simple as Eric's, because Eric's just has one scenario that works for everything. Well, in this case here, this algorithm evaluates three different scenarios.
Mm-hmm. Yeah, I mean, I think if this was the first go at the problem, I don't have too much issue with it, I guess. But I think just maybe from an approach standpoint, see if you can reduce the number of kind of cases. I mean, obviously, depending on the question, there's edge cases that might need to be handled, and you have to always consider those. But I think, yeah, just if you can reduce the complexity by reducing the number of, I guess, cases that it checks, and you can reduce that down to, something more generic, that's always better, because otherwise you have too many conditions to kind of evaluate through, and that inadvertently sometimes it leads to bugs as well, or other cases you don't catch because you're trying to be too clever.
Yeah, absolutely. I do have one nitpick here as well, and actually this is important because it goes towards simplifying code and kind of understanding what the semantics are, right? So see here, we have this variable called inc, or increment, I guess, right? That's how much you're going to be incrementing, right?
Mm-hmm.
So start off with one, and then that incrementer is incremented here. But basically, what you're doing is you're always using that inc together with piles.getI. So that's the rate that you're looking at, right? So rather than having a variable called inc, I would instead use a variable called rate, at the rate at which you're eating. And then the rate would be basically this, right? Whatever piles.getI is plus and then you're incrementing that rate. So instead of incrementing an incrementer variable and then adding it to something else, just have your rate and your incrementing rate. So same with this one here on this section here. It's the same. It's the same. It makes it that much harder to read because now people are trying to remember, okay, now I have an incremental variable, incrementer variable, and I'm adding it to this. Will the incrementer variable be used for something else, right? But if you have a variable just called your rate and then you're only incrementing rate, then it makes it that much simpler and easier to understand. Yeah, so that's I guess a nitpick, but also a good principle to consider. All right. Should we move on to the next one?
Yeah.
Okay. Oh, okay. There's an extra evaluate speed here. Actually, one more nitpick since. So evaluate speed here is a utility function. My nitpick here is on the name, because you're not actually evaluating speed. What you're doing, what you're trying to do is you're returning the number of hours needed to consume all these nuts given this speed, given that rate of consumption. So given this rate of consumption and this pile of nuts, you want to return the total hours needed. So that function name evaluate speed doesn't tell me anything. Maybe like it's a longer name, but something better would be like hours needed to consume, right? Hours needed to consume, and then you pass in what you're consuming and the rate that you're consuming it at. Then it's very clear when I read that, okay, you're giving me back the total number of hours needed to consume these nuts. Okay, so, all right. Okay, let's go to submission 3. This is submitted by Faizal. Okay, I'll let you get it first dibs on this.
Well, we were discussing about this problem actually before we started recording, and I guess our nitpick is we see that it works for our input set, but if we were to swap it out, we're not sure if this solution would work in different scenarios or with different input. And the problem that we had when we're trying to figure out what's going on here is that there is a lot of different, like if we look at the right side, kind of to the bottom right, there's a section called calculations to adjust our feed rate. But I'm not quite sure where or how he came to this conclusion of like what he should be doing here. Like, what's with the multiply 1.5 plus equals 1.5? Like, I guess it's not really clear. Where he got that, I guess, algorithm of sorts to get those numbers to calculate the feed rate. We're not quite sure. So Faizal, good job in that it works for our input set, but again, we're not quite sure. Yeah, like if this was a different input set, if it would work, and I guess where this algorithm, how you came to this conclusion.
Yeah, that's my feeling too, Faizal. So step by step, I can understand what each line does, but put together, I don't understand why it works. Now, I know if I run this, it gives me the right answer. So at least for the data sets that we have. But I, like Ronald said, I don't have confidence that this will work for all data sets. And the reason for that is because even though I understand step by step what it does, in totality, I don't understand why it works. Why does this algorithm here, where you take the number of hours subtracting the size of the number of piles and adding 1, how does that give me the answer here? Like the explanation here, you're referring to an inspiration, but it doesn't explain to me how that works. And the same with this second algorithm here. your explanation is by experimentation, and that's fine. That's part of the scientific method, right? Experimenting and finding a pattern. But once you found the pattern, you need to be able to describe how that pattern works. And so you found a pattern, but we need that extra step to understand why that pattern works. And it's good for you too to kind of work that through in your mind. Why does this pattern work? Because you have to convince yourself that this algorithm works for all data sets, right?
Mm-hmm.
Yeah.
And I mean, sometimes like in my work, like I would encounter some code that, you know, it requires a special kludge or a hack to work around some issue. And, you know, those things do happen in real life. So I guess it's not to say that it's not strictly not allowed, but I think it's important to also explain why this works, because like, yeah, I guess kind of like what Roland was saying, like, yes, you experimented and it works, but then you need to explain why it works, because otherwise when someone else comes along with and you know tries to use this code, they don't understand why this was implemented at that time to make it work, right? So yeah, I think explaining why you did and how you explain it is just as important as the solution itself, if you're going to go through with a weird workaround.
Yeah. Okay, awesome. All right. And then, yeah, there's just the last remaining code for Faizal's. Actually, do you want to say something here for this one?
Yeah.
Okay.
Yeah, we were also looking at this this portion here, and the thing he was doing here is to round it up if it is a decimal. Now, this totally works. Like, so he checks if the modulo 1 is greater than 0. So that indicates that, you know, when you divide it by 1, it doesn't divide properly because it's a decimal place. And if that's so, then you round it up. But you could have simply done like a math function to just take the ceiling of it or something, which is way more easy, and it's one line, and it's like it's more defined than doing this roundabout way to calculate the ceiling of the number. So yeah, just I mean, it works, but I mean, it's like kind of like when you have a hammer, everything looks like a nail to you. Yeah, it's a very clunky way to do it when you can do it in one line with a built-in function instead.
Yeah. Okay, great. So let's move on to the next one. Faizal, or anyone watching this, if you have any comments or you disagree with what Ronald said, please leave us a comment. We'd be happy to engage in a conversation with you. Okay, so this submission, the last one that we're going to go over tonight is from Mackenzie. So yeah, I guess Mackenzie here, based on his comments, and I understand how this works. So he's using some sort of binary search to kind of iterate through and figure out what is the minimum rate. Now, there is a problem with this algorithm though, Mackenzie, in that one of the data sets this fails for this problem here. So in this data set with 6 hours with these 5 homes, the minimum rate should be 23, but in your algorithm you returned 22. Okay, and I think so that's an off by 1 error, and I think it'd be good for you to look at this again and see if you figure out where you had the off by 1 error. Could it be somewhere here, or could it be somewhere in here? So you had an off by 1 error just for that one case. For all the other cases, you got the right answer. So yeah, what are your thoughts, Ronald?
Yeah, I mean, for that off by 1 error, for our input sets, just because generally they're pretty small, I always encourage you to double check your answers, and you could have easily gotten the full points for this if you just did a simple check. So yeah, I mean, that's the first thing. The second thing is nothing wrong with using binary search, but also I don't think the problem really requires a binary search approach unless, I think last week someone, I can't remember who it was, but someone also did another search trial thing and they were trying it out to learn. I mean, nothing wrong with that, but I think, if you saw this problem and you immediately jump to a binary search approach, definitely consider other approaches before you do that, because especially with these kind of leak code style problems, these algorithm style problems, a lot of times there's a specific almost approach that they design the problem around. So and in some cases, there's one way almost. I mean, there's multiple ways to do it, but there's one way that is the most optimal. So yeah, if you're doing this for fun and learning how to do binary search, great, no problem. But if this is your first, this is the first conclusion you jump to right away and that's the approach you took, definitely reconsider other approaches, because a lot of these problems, they have kind of one or two optimal ways to solve it.
Yeah. And kind of just adding on to what Ronald said is that, when I'm evaluating code, like through a code inspection or something, I always think is this the simplest solution, right? More often than not, usually the simplest solution is the best solution, for a couple of reasons. So potentially, this could be slightly more optimal than a linear search, like you mentioned here, right? Potentially, it could be slightly more optimal in terms of performance, but because of the complexity, it's harder to see if you have an error. So for example, you have an off by one error and you didn't see that right away because you can't tell by looking at the code because the complexity hides it. But if the code were simpler, like for example, in the first submission and Eric's code, the logic is so simple that it's there's a higher chance that you'll see, oh yeah, this logic, I missed something here in that logic. So it's, and also because it's the more complex the code is, the higher chance that there is of a bug being introduced. And you've probably already heard this principle, right? The KISS principle. Keep it simple. So it should be stupid, but I'll say keep it simple, silly. and that's a principle that many engineers live by, because most often than not, the simplest solution is the best solution. So that works equally well for bridges, for buildings, and also for production code. So it's something that you should really think about. Is there a simpler way of doing this for maintainability as well, right? Someone else, either you coming back to this a few months later, or someone else maintaining your code a couple of years down the road, you will really appreciate it if it's simple. Okay. All right. So I think that's all the code that we're reviewing today. Any final words, Ronald?
Yeah, I mean, we're in the home stretch. I think we have just one more problem for everyone to solve. So keep up the good work. Yeah, I mean, obviously everyone's busy with trying to get their projects up and running before the deadline. So no worries if you don't have time to approach these problems live. I mean, they're always going to be available for you afterwards as well. So if you want to attempt them later, by all means, go ahead and attempt them. They're available for you even after. So no worries if you don't have time and you're busy trying to get your projects done.
Okay, awesome, great. Okay, thank you, Ronald, and thank you everyone for tuning in. And we'll talk to you next time. If this video was helpful, please give us a thumbs up. Feel free to leave us any comments if we said something that you don't agree with or you want to challenge us or something. Otherwise, we'll see you soon. Take care.